Okay, hello, and thank you for the introduction. Thank you for ThinkyCon to arrange this convention for online convention because I can join from Singapore, which is unfortunately 2:30 in the morning, but I'm still excited to give this talk. I'm Ivan Kosora, online more known as Chaotic Ayak, and I'm going to present about mathematics for puzzles. I want to talk a bit about me first. So this is ThinkyCon. This is by Thinky game developers for Thinky game developers. Well, I'm not really a game developer, but I am Thinky. I write puzzles. The puzzles I write are logic pencil puzzles, things like Sudoku, Kakuro. I think you're familiar with it, although my kind are kind of different. I've written several puzzle contests, and if you are interested to see my work, you can find my website chaoticayak.github.io. There's a logic archive section where I have all sorts of my logic puzzles over like more than 10 years by now. So now to the talk. If we are talking about puzzles for mathematics, there have been a lot of research about it. For example, puzzles train your critical thinking, puzzles train your problem solving skills. And mathematical topics are usually abstract, it might be hard to understand. Puzzles help give you a concrete example, concrete situation, so it's easier to understand. Puzzles also satisfy a pattern I call rules, deduction, solution. You're given the puzzle rules, the game mechanics, you start building up small deductions, larger deductions, you chain them together into a solution. It is exactly just like math. But this the topic of this talk is mathematics for puzzles. It's the other way around. So I want to talk about mathematics for puzzles. In this talk, I will give you some examples of what kind of mathematics you can find in puzzles. And then I will show you some more examples and even more examples, even in things that you don't expect. And that's basically the point of this talk. I want to just share a lot of examples. And for you, you are not supposed to take the examples as is because your game rules are different, your game mechanics are different. But I want to encourage you to think about your own rule set, think about your game mechanics and its implications. See if you can find anything like this. And as a logic puzzle guy, I will talk a lot about logic puzzles in this talk. It should also be applicable to games. We will also discuss a few games. And unfortunately, I don't think I will have enough time for questions, but please do ask questions on the live chat or on the Discord, and I will answer them after the talk. We will begin this talk with a puzzle. Here's a 5x5 grid of rooms. I want you to draw a path from the start on the top left to the exit on the bottom right, on bottom left. And you may not retrace your path. The white rooms must be visited exactly once. What about the blue rooms? The blue rooms are ice. Ice is slippery. You cannot turn on ice. You must go straight. The ice rooms must be visited as well, at least once, but you may visit it twice if you visit it is in a cross, like once horizontally, once vertically. And that's all the rules. You can, if you want to try, you can try it. There should be a link posted in the live chat. Unfortunately, I will not be able to wait for you to solve it. So you can look at it, you can give it a thought, and I'll continue talking. So this is a mobile game called Alcazar. Unfortunately, it was discontinued in 2017, but when I played it, I found it enjoyable. And a puzzle looks like this. The goal is to draw a path from one exit to another that visits all the cells exactly once. For this puzzle, the solution would look like this. From one exit to another, and you visit all the cells exactly once. Now, if you look at this puzzle, it's a screenshot from the actual game. You can see the cells are colored slightly differently. Some of them are dark, some of them are light. Why is that the case? Is that just for decoration? Turns out, no. That's to help you do some math in Alcazar. Something called parity. What is parity? The idea here is that the path is going to alternate between dark and light cells. From a dark cell, you move to a light cell, you move a dark cell to a light cell, and so on. It just keeps alternating. And you can make use of that. For example, in this puzzle, you can see there are 12 dark squares, 12 light squares. Then you know by using parity, the start and the end are going to be on opposite colors. One of the exits is on the top right. I think it's very obvious it's going to be used. This exit is on a light square. Because we know the two exits are on opposite colors, that means the other exit that is on a light square here on the bottom left will not be used. That's how you can use parity. One way you can use parity. Now let's talk about a puzzle that I make myself for this talk. Unfortunately, it doesn't look as good as Alcazar, but we'll make you do with it. If you don't know anything about parity, this is all you can do. Draw the corners. You have to visit the corners so you can draw these lines, but without parity, this is all you can do. You are stuck. So let's try to use parity. If we look at this puzzle, there are 13 dark squares, there are 12 light squares. That means the start and the end must be on dark squares because there are more dark squares than light squares. So there are only 2 dark exits in this entire puzzle here on the top, and there are a lot of light exits, but none of them is used. We can just basically draw walls on them. And that's how you can use parity in one way to use parity. By using these new walls, you can actually draw a few extra segments on the right side, although you're still stuck. That's just one way to use parity. We are going to use parity again. Now, we have been using parity on the whole board, so let's look on a smaller area. Here, this green area over here on the bottom left, it must be visited. It has 2 dark squares, 2 light squares. Then, by using parity, you will be able to tell there must be at least 1 dark exit. But there's only 1 dark exit in this area, the one I marked with a red segment. And so, what next? We can do it again. We can do parity again on this larger area. Again, draw a new red segment. And this kind of deduction is known in the logic puzzle community. They gave it a name. It's called parity bouncing. You are using parity over and over again in larger and larger area. You keep drawing lines around, and these lines are kind of like bouncing around the grid. And this new segment is important. Why? Because by drawing this segment, you just made a new corner. And by drawing this corner, you resolve the entire bottom left part. And now you suddenly have something that is almost completely a loop. You cannot have any loop in the board. You have to have a path connecting all the cells. So you have to avoid the loop, and suddenly the puzzle solves itself. But without knowing parity, you have no idea how to solve this puzzle. With knowing parity, with knowing this kind of deduction, suddenly the puzzle becomes solvable. You can actually do the puzzle. And what about the puzzle that I gave you earlier with ice? Well, we have been talking about parity. Let's try to use parity. Now, the start and the end are on like squares. So the number of like squares will be dark plus 1. The problem is if you count it, there are 12 like squares, there are 13 dark squares. You have to visit all the cells, so you will have 13 dark cells. That means 13 plus 1 is 14. You only have 12 like squares. What can you do? Well, remember ice? Ice allows you to cross it twice. So if you cross a cell, you are basically counting the cell twice. And that's what we want to do. We are going to cross on both like rooms. Now, we have 14 like squares, 13 dark squares. That's enough. 14 is 13 plus 1. And this is all the light cells that we have. There's no more crossing on lights. That means we cannot increase the number of dark cells. We cannot cross on the dark cells. By drawing these lines and these walls, you will be able to solve the puzzle. You can try it. So again, here, what we are doing is we are using parity in past puzzles in Alcazar or in my puzzle with ice. And one important thing about this is that the rules don't actually say anything about parity. The rules are just visit all cells. And suddenly parity comes out and say, oh, you can solve this using parity. And yeah, so the rules don't say anything. You have to recognize it yourself. And in a sense, this feels a lot like math or puzzle in general. The problem statement, whether it's a math problem, it's a theorem you want to prove, or it's a puzzle you're facing, might not say anything about the solution. And you have to think about this. And we've been talking about parity in past puzzles. What about other kinds of puzzles? Turns out parity is very powerful. It can even be applied to things like this. I think a lot of you are familiar with this game, A Monster's Expedition, really good game. Alan gave a talk about the editor of this game yesterday. Today, I'm going to talk about of the design of the puzzles, the game mechanics, analysis of the game mechanics. So turns out you can do parity in a monster's expedition. This time the parity is not going to be on just 2 colors, it's going to be on 4 colors. Here on the purple square, let's imagine a log that is standing upright. If we push it forward, then it's going to lay down vertically, and it is going to be on a red square. If we push it forward again, we are standing up the log, and it's going to be on a purple square. So like on a purple square, it's going to stand upright. On a red square, it's going to lay down vertically. You get the idea? If you push it sideways, it's going to lay down horizontally on a blue square. And if you try to push it onto a white square, well, it's going to roll off forever. On a white square, it cannot stay still. And that's our parity, our fourfold parity: purple, red, blue, and white. Let's use this to solve an actual level from the game. This is an actual level from the game. It's early level. You will find it in a few minutes. So if you don't want to be spoiled at all, please turn away for now. But I think it's fine to spoil something like this. So this is the level. The goal is to get the log over to the left row, and you have to do it in a horizontal way so that you can cross it to the next bridge, to the next island. But if you try to color it with our parity coloring, turns out the goal square is red. Red means it's laying down vertically. That's not what we want. We want the log to be horizontal. So we have to change the parity. How can we change the parity? Well, there's one thing we can do to change the parity. We said that on a y square, the log should not stay still. But if we bump to a block, then we force the log to stay still. If it happens on a white square, that means our coloring suddenly becomes wrong. And when that happens, we are going to change the entire coloring. So here's an example. If we push the log forward, and then we push it all the way over to the right, then it bumps to a block, it stops. But it is on a white square. Well, it just means the coloring is wrong. Now the log is vertical, so it's supposed to be on a red square, and the entire coloring changes. Now you can see the goal has changed color. It becomes white. This is still not enough. We have to change the parity once more. We can do that by going up and then pushing it 3 times to the left and then bump it down. It bumps again to the stump of the log, and this is again on a white square. It changed the color again. Now this is laying down horizontally, so it has to be horizontal. It has to be a blue square. Now the goal becomes blue, which is what we want. The goal says we have to, the log is going to be horizontal here, and that's what we want. We just push the log over to the left. And so by using this idea of parity, you can realize that, oh, we have to change the parity. So it's easier, it's more manageable to figure out what we want to do for such a level. So parity, a lot of applications in math, it's very useful in so many different fields. A lot of applications in puzzles as well. There are a lot of different puzzles. We've talked about Alcazar, my puzzle with ice rooms. In general, it works for past puzzles, and in general, and even works for a monsters expedition. Something that I don't think a lot of you realized. I don't think a lot of you would imagine to work. And I earlier said that the examples in this talk might not apply for your game, but I think Parity is very powerful and very broadly applicable that it might actually apply for your rule set. There's no harm in giving it a try. Try to explore it, whether you can find any kind of mathematical theory based on parity. And once again, the rules of these games: Alcazar, visit all the rooms. Pet puzzle, my puzzle, visit all the rooms. A monster expedition, just push locks around. The rules don't say anything about parity. You have to recognize it yourself. Okay, let's move on to a different thing. It's called Nurikabe. A Nurikabe puzzle looks like the one on the left, just a grid with numbers, and the solution is on the right. You can see you have to shade some of the cells black so that each white island has one number which is equal to its area. Now, all the black cells have to be connected, but you cannot have any 2x2 area of black cells. Now, I know a lot of you are playing Islands of Insight. There's even a talk by Elliot just following me. So I grabbed the rules from Islands of Insight. These are exactly the rules of Nurikabe. So yeah, this is about Nurikabe puzzles, and then I wrote this one puzzle, and then gave it to some people. One thing you need to know about logic puzzles is that they are supposed to have exactly one solution, not just a solution. That's all puzzles want to have a solution, but exactly one. There should be no alternate solutions. There should be no ambiguity. So I made this puzzle. I gave it to people. They are usually able to find one solution, find the solution, but they are having trouble to prove that it is unique, that it is the only solution. So they find the solution by using intuition instead of logic. So how can I be sure that there is actually exactly one solution? Well, when I tried things around, I made several different wrong answers, and in each one of them, I see there's a 2x2 area of black cells. There's a 2x2 area. There's a 2x2 area. There's a 2x2 area. And I started getting the intuition. The islands are very small. It is hard to reach everything. That's why we keep getting places where no island reach it. That's why we end up with 2x2 areas of black cells. And from this intuition, I started forming a rigorous mathematical argument. I called it grid point counting. What is grid point counting? The idea is I want to count the grid points that are touched by an island. So this island of size 1 touch 4 grid points. This island of size 3 touch 8 points. For size 4, you can touch 10 points on the bottom right or 9 points on the top left. In general, size n will touch at most 2n plus 2 points, which you can prove using mathematics. Less if the shape is wrong in a way. I will talk about it later. Why am I so much interested in these grid points? That's because some observation that I noticed. Let's look at a grid point inside the grid, so not on the boundary. If there is no island touching it at all, that means its entire everything around it is black. But if everything around it is black, that means it is a 2x2 area of black cells. That's why I'm really interested in these grid points, because all the internal grid points must be touched by islands. Otherwise, we have this 2x2 area of black cells, and Norikabe rules say we cannot have that. So back to the puzzle. I look at it. There are 36 internal points. We have to touch them all. From the islands, we say size n is at most 2n plus 2 points. So size 4 will give us at most 10 points, size 5 12 points, size 6 14 points, in total 36 points. There are no hidden islands. Each island must contain one number. So there are no hidden islands. These are all the islands we have. So we know there are 36 points available from the islands. And wait a minute, there are 36 points we have from the islands, and we have to use them all to touch all the internal points. We cannot waste anything. And that's the basic idea behind the argument. How are we wasting points? Well, there are three ways to do that. I call them defects. The first one is if an island has a 2x2 area, then it becomes more compact. It touches less grid points. Like this size 5, normally you can touch 12 points with that, but due to the 2x2, it only touches 11 points. The second defect is if islands touch diagonally. Then you have two islands that are touching the same point. What is that for? You only need each point to be touched by an island. Why do you have two islands touching it? That's a waste where you could have touched something else. The third defect is if an island reaches the edge of the grid. That's also a waste. We only need to cover the internal points. Why are we using points on the boundary? So those are the ways to waste grid points, the kinds of defects. And in our puzzle, I said there are no defects. The first so each of these three defects do not happen. The first defect is actually not very useful in this puzzle. It's the other two defects that are useful. For example, the second one say if islands touch diagonally, that's a defect. We cannot have that. So these cells must be black. Otherwise, they are islands that touch diagonally. The third defect says that an island that reaches the edge of the grid is a defect. We cannot have any defect. The entire border must be black. And by using this, by avoiding all these three defects, you can actually solve this puzzle logically. Like logically, without the need of intuition, you can prove that it is unique. And one important thing to note is that these defects just appeared out of nowhere. The Norikabe rules don't say anything about avoiding these defects. It's just our arguments. And just to recap, the grid point counting is my discovery. It is specific to Norikabe puzzles, unlike Parity that was very broadly useful in all sorts of puzzles. This argument is only for Norikabe puzzles, and even then only for puzzles of a specific structure where the islands feel very small. And the idea behind the argument is that I got the intuition of it's hard to reach everything, and I turned it into a rigorous math proof. Because I have a math proof, I am confident it is correct, I can make use of it as for puzzles. And there are a lot of other examples in the logic puzzle community and even in games. Like you can use topology, you can use graph theory, and similar to grid point counting, there are a lot of different kinds of arguments as well. I would have loved to talk even more about that, but well, I'm running out of time. It's okay. Once again, these examples are not meant to be used as is. The examples might not apply to you because your rule set is different. I just want to encourage you to think about your own rule set, figure out implications, dig deep, figure out if there's any kind of hidden theory inside. Often the theory is based on mathematics. And if you can get that theory, you can figure out a puzzle from it. It often leads to very satisfying insights. And so that concludes my talk. Thank you for listening. Once again, I don't think I have time for questions, but ask them on the live chat or on the Discord, and I will be able to answer them. And yeah, thank you for listening.
Thank you so much. That was absolutely fascinating. I always wish whenever I'm doing logic puzzles, I always wish I could do this better and like use math to help me prove some of the things out. And I often just go on intuition alone and wishing I could.
Yeah.
Thank you very
Okay.
much, Chaotic Ayak, for joining us.
Yes.
Thank you so
Yeah.
much.
Thank you for having me.